It's a real pleasure to be here and tell you about work that we've been doing on computational approaches to understanding the properties of materials. And I really want to thank the organizers for their invitation. This is a second or maybe third TAMEST meeting that I've been to, and I've certainly enjoyed them all. I want to talk about an issue that's been in the literature for over 80 years. And it has to do with some comments that were first made by the very famous physicist P.A.M. Dirac. And I've called what he said Dirac's challenge. And in particular, I want to talk about Dirac's challenge as applied to materials. So I better tell you what Dirac said. He said that the underlying laws, physical laws necessary for understanding a large part of chemistry and the whole of chemistry are known, not just completely known, not just known, but completely known. Okay? And he said that the only difficulty in dealing with these equations is that they're much too complicated to be solved. Now, that's not a very encouraging comment, because he's basically saying, I know the answer, but we can't do anything with the answer. Well, that's a little bit unfair. It's unfair on two counts. First of all, his point in making this statement was that the situation in many ways was analogous to after Newton developed his equations of motion. Because of Newton's laws, we're able to understand planetary motion, we're able to understand how classical objects interact. And what Dirac's point here was shortly after the invention of quantum mechanics is that we were in a similar situation. We could understand how to compute electrons, nuclei, atoms, molecules, how they interacted, which is all of chemistry. But not all is lost. If you go on and read what Dirac says, this is the part of the quote that's the most famous. The second part of the quote is where he gives us hope. Because he said, it becomes desirable to find approximate practical methods for understanding the main features of complex atomic systems. Now, I cheat a little bit, because, you know, it's those ... there. And actually, the ... says without too much computation. Now, don't forget, this is circa 1929, and so too much computation was probably something other than a slide rule. Well, we're going to do a little bit better than that. We're going to look at computation that involves computers. But the thrust is the same. This is what I've called Dirac's challenge. What sort of practical quantum mechanic methods can we develop to really understand much of physics and all of chemistry? Well, the equation doesn't look all that difficult. It's usually written H psi equal E psi. It's a complicated equation because it has this Laplacian operator here that makes it a complicated equation. It's a partial differential equation. Now, the first thing that you might know that annoys everyone is you've got R1, R2, R3 here. This is the total number of particles in the system. Now, I'm going to be talking mostly about electrons. And so if I have a macroscopic piece of material, I might have 10 to the 23rd electrons. It's a lot of electrons to deal with. Fortunately, it's not all that bad, because typically, if I understand the behavior maybe of a few thousand electrons, and a few thousand atoms, I can understand what's going on in a particular material. The second part is really annoying, too, and that is dealing with the quantum nature of the interactions. These constituent electrons are not classical particles like an apple or an orange. They have very unusual properties, and I'll talk about that in just a second or two. Another annoying thing is even if we solve this equation here, the E here is for the energy. Okay, that we can understand. Add up the total energy, kinetic energy, potential energy of the electrons. That's not such a big deal. What are these psi here? These are wave functions. So what do they mean? And how do we interpret them? Another annoying thing is that the length scales involved here for different electrons are very disparate, the length and energy. If I look at a lead atom and I look at the most tightly bound electrons in lead, they're orbiting around the nucleus, they're moving at relativistic speeds. And they're very localized next to that nuclei. The outermost electrons in lead that do all the work in forming a chemical bond, they're not moving at relativistic speeds, and relatively speaking, no pun intended, they're pretty spread out. So I've got very different types of electron states. And then this is a really annoying thing. I need a very accurate or precise solution. If I take a piece of silicon and I have a silicon atom and I ask a very simple question, would that silicon atom rather be part of the crystal or would it rather be in isolation? If I can't solve an equation like that to within, say, 0.1% in terms of the accuracy, I can't tell the difference. That's bad. I could do all this computation and not even be able to tell whether silicon's going to want to form a solid. So the situation doesn't look so good. And if we start asking questions about, well, what do we mean when I say that these constituent electrons are not classical objects, the situation isn't improved by very much. So let me ask a simple question. If I have an electron and it's confined maybe over a nano scale, and I say, simple question, does the electron act as a wave? In other words, if I think of a light particle, could I diffract it around a barrier? Or do I think of it as a particle that it hits the barrier and just stops and it casts a shadow? So the question is, are electrons particles or waves? And the answer is yes. This is a problem because it means that I can't treat electrons as classical objects. I can't say that there's an electron at a particular position, X, Y, and Z. And it gets worse because traditional quantum mechanics tells you that I don't even know the position of the electron precisely. There's the uncertainty principle that's involved, which I'll talk about a little bit. And then there's another issue that comes into play, and that is a probabilistic interpretation. So I have to do a bunch of measurements just to determine where that electron might be. So if I have an atom or a molecule and I say, well, where is the electron relative to the nucleus? I don't really know. So I'm not going to go into a great deal on the philosophy of quantum mechanics. I love this quote here from Einstein, who said that he liked to invent phases. It was a little before my time. But he would say things like, God does not roll dice. There's God rolling dice. And he would say things like, the Lord is subtle but not malicious. I hadn't realized until recently that Bohr got sort of annoyed, Bohr being one of the founders of quantum mechanics, and said to Einstein, stop telling God what to do. Okay, well, we're not going to get into a philosophical discussion. We're going to assume that these equations of quantum mechanics can be useful. But useful in what sense? And how do we really know that these quantum mechanics can tell us anything? I heard someplace a talk that 40% of the electronic devices like this, are based on quantum mechanics. Now, I would have said everything's based on quantum mechanics in the sense that without quantum mechanics, you couldn't understand the chemical bond. And if you can't understand the chemical bond, you can't understand matter. Okay, let's not get too carried away. I want to give you one example, a couple of examples of the consequences of quantum theory. And one is a very simple thing. Let's look at the electrical conductivity of elements in the periodic table. Now you look here, and the first one I have listed here is silver. Silver conducts more electricity more readily than any other element of the periodic table. In units that involve reciprocal ohms, reciprocal meters, it's almost 10 to the 8th. If you go down the list here, bismuth isn't such a hot metal, so it's not as good. Germanium's a semiconductor, so it's down about maybe 6 orders of magnitude, 7 orders of magnitude. Sulfur's 10 to the minus 16th. The span I have here is roughly 24 orders of magnitude. 24 orders of magnitude is a big number. The way to get a picture of what that actually means is to think the following. The diameter of a galaxy is about 10 to the 21 meters. The head of a pin is about 10 to the minus 3 meters. So the length scale spanned from the head of a pin to a galaxy is 24 orders of magnitude. That's what we got in conductivity. Now, if we can't deal with a situation like that, where I've got 24 orders of magnitude, and I can't explain that, then we're going to have a problem. So let's see if quantum mechanics can explain something. By the way, this is one, other than distances, astronomical distances, of physical properties. This is about the largest span. Okay. Well, let's think about how solids are formed. And I'm going to be dealing mostly with crystalline material or solid-state materials. So we could say, well, imagine I have an atom. It has some energy levels. Because of quantum mechanics, these energy levels are discrete. They might be separated by a few volts. I bring another atom into the system, and I get some extra levels. I double the number of levels, but I still get spacings between these levels. I keep doing this. I bring in 10 to the 23rd atoms. I can still have gaps, forbidden regions, between the energy levels. What does a forbidden region mean? Well, it's not like a military thing. It's not like a DMZ or something like that. But what it means is that the electron cannot exist in an eigenstate. It can't solve that Schrodinger equation and have it have that energy. So we can get these regions here where I have a lot of energy levels. These energy levels are called bands. I think I put that down here someplace. And these bands are separated by these forbidden gaps. Now, within a band, the average energy difference can be on the order of maybe 10 to the minus 8, 10 to the minus 10 electron volts. Let me tell you, you're not going to measure it. Okay? So, for all practical, or the differences between those levels. So, for all practical purposes, you have allowed regions where the electron can have any value, and then you can have empty regions. Well, what happens that make these 24 orders of magnitude difference in solids is how these energy bands are arranged. So here's an example. I think Emily Carter showed you a very similar plot yesterday. Typically what happens is let's go back. Typically what happens here is that these filled bands, they're called valence bands, very cleverly made up of the valence electrons. Then there's a gap, and then there's something called conduction band. Not surprisingly, conduction bands are called conduction bands because if you put an electron in said band, you can move it. It can conduct electricity. So if you look at a piece of sulfur, let's say, that has a band gap of maybe on the order of 10 volts, that means to take a valence electron and move it across this gap takes a ton of energy. That's why the material looks transparent, because light, what your eye can see, is about 1.5 volts to 3 volts. So if I bring an electron, a photon, it doesn't have enough energy to make this thing do anything. A semiconductor like silicon has maybe a couple of volts. That's why semiconductors are so great. You can put a battery on it, put a few volts across it, move things from the valence band up to the conduction band, and build devices. On the far right, I have a metal, and that is there's no gap. Now, sometimes you'll see textbooks that'll still label this as a valence band. It's not a valence band. Once you get band overlaps and one of these bands is not full, this whole complex is called a conduction band. So we have metals, semiconductors, insulators, and that accounts for the 24 orders of magnitude. Okay, now, oh yes, that was my little mnemonic to get you excited about gaps. Because that's what I'm going to focus on. I could focus on a lot of different things, but I'm going to focus on the gap. Okay. Now, just as the conductivity changes between solids, so does the optical properties. If you look at something like a piece of ice or a piece of window glass, it's transparent because those photons don't have enough energy to make a transition. And quantum mechanics says, no, you've got a forbidden gap in that region, and if you have a 3-electron photon come in, it's not enough to do anything, zips right through it, and that's why this material is transparent. Silicon has a small band gap. It's about a volt, and therefore, if you try and move light through it, it doesn't go through it. It looks gray and dark, and this is the stuff of our generation, by the way, because this is the electronic material, and we really do live in the age of silicon. Most of the materials I'm interested in, by the way, are electronic materials. Let me show you another example of how quantum mechanics can help us understand things. Again, just qualitatively. Okay, here there are a bunch of vials. The vials contain hexane, and in that hexane there's cadmium selenide. You notice all these vials have different colors. You might say, oh, they have different chemical compositions. No, they don't. The stoichiometry of these materials is exactly the same. The only thing different is the size of those cadmium selenide crystals. They're nanocrystals. Maybe they're on the order of 10, 20, 30 nanometers. Why is it that they have different colors? It's great. We can change the physical property of a material just by changing its size. But why would one of them look red and why would one of them look blue? Very simple quantum explanation. Many of you have heard of the uncertainty principle. It says, if I don't know the position of the particle and I don't know the momentum of the particle, the air in the position being, say, delta x, the air in the position being delta p, that has to be, the lowest product of that error has to be on the order of Planck's constant. Planck's constant is an incredibly small number. If it were 0, we'd do away with all of quantum mechanics. It's not 0. So what it says is that momentum scales as 1 over the localization. And if we make an estimate for the energy, we'll say, well, the kinetic energy is the momentum squared, and the momentum really can't be smaller than the uncertainty in the momentum. So that energy is scaling like 1 over x squared. It's like a particle in a box. So if I really squeeze down on that electron, I make that cad selenide crystal so small that the electron is unhappy, it's quantum confined, the energy gaps start to change. And they'll change from red to yellow to green, blue, indigo, as the gaps get smaller and smaller. Okay, so these are some examples of quantum mechanics that arise simply because there's a gap. I had all sorts of these things. One of them was I was going to show you the heat capacity. You can say the heat capacity, well, that's very different than an optical excitation. But Einstein in 1907 showed that the heat capacity went to 0 because there were also quantized vibrational modes in crystals. You don't usually think of thermodynamics related to quantum mechanics, but it is. And that advance really saved thermodynamics, if you like, because if the heat capacity doesn't go to 0, at 0 temperature, it's very, very hard to talk about things like entropy. Okay. Let's move on. So I want to talk about practical quantum mechanics. So can we use methods to calculate these gaps? We have an enormous number of applications if we can do it. Well, this is a talk in and of itself, so I'm going to just give you a few ideas on what sort of practical quantum mechanics I mean. There are three physical concepts that I'm going to invoke to do practical quantum mechanics. The first one is to consider one electron at a time. So I'm going to average over all the positions of the system and see what their impact is on one electron. Typically, that's can be justified by a Hartree or Hartree-Fock approximation. We won't go into that. The second thing is we're going to use what we can measure. Now, I purposely mentioned wave functions early on when I showed you that Schrodinger equation. Wave functions really are at the heart of what we don't understand, or maybe people don't feel comfortable about quantum mechanics. I can solve for a wave function. If I square that wave function, it'll tell me where the probability is of finding an electron. Probability is a sort of a strange concept too if you think about it. The only way I can talk about a probability is if I do a measurement. And so quantum mechanics and measurements are very entwined. But let's not worry about this except to say you can't measure a wave function. Really odd if you think about it. There are things in quantum mechanics you can measure, like energy, probability of finding an electron, and there are things you cannot measure, and one of them is a wave function. So we're not going to use wave functions. We're going to use density function. Oops, I did it again. We're going to use density functional theory, and that is the wave function squared. That gives a density probability of finding an electron. The third one is actually the one that's nearest and dearest to my heart. Remember, I told you we had those crummy disparate energy and length scales, that the electron around the nucleus of lead was moving like a bat out of hell. It was relativistic speed. It was highly localized. I don't want to deal with that. I only want to deal with the outer electrons. So you can make a transformation with those inner electrons and the nucleus and end up with a potential. It's called a pseudopotential. I don't like pseudopotentials. I don't like the name pseudopotentials because it implies pseudoscience. We are not doing pseudoscience. Trust me, it's okay. But it'll allow us to treat carbon and lead on equal footing because they have similar outer electrons. Okay, I'm going to show you one equation here. This is the so-called Cohen-Sham equation. It involves density functional theory. So let's look at it for a second, and I'll tell you why it's hard to solve, but once we can solve it, we're in business. This first term here, this Laplacian operator, represents the kinetic energy of the system. Then I have three potential energy terms here. The first one is that pseudopotential. It's okay. It's the nucleus plus the inner bound electrons. The second term is the electrostatic. That's just classical Coulomb's law. If I have an electronic charge density, I can add up what that potential is being. Where do I get this charge density? Well, this is an eigenvalue problem. I take the wave functions here, I square them, because that's what counts, and I sum over the occupied state, so I have a neutral system. That gives me a charge density. Aha! If I know that charge density, I can calculate the Hartree potential. This term over here is the kicker. It's the one that this fellow Walter Cohen and others developed. It gives you the behavior in an approximate sense of these non-classical interactions between the electrons and the system. It's called the exchange correlation potential. All it depends on is the density in the simplest form. Where do you get this from? It's one of these things that's not known, and it may not even be knowable. You can calculate it in limiting cases, and then you assume it's okay for everything. All right, now when I first looked at this and I was a student, I said, this doesn't look so good because I need this charge density here to get these two potentials. But to get the charge density, I need to know the wave function. But I don't know the wave function because I don't know the potential. So we're going to have to solve this problem in an iterative fashion. And let me show you what I mean by that. Here's a flow diagram that shows how to do it. We're going to guess at the potential for the atom. The atom is easy to solve. It's not like a molecule or some of these other things. I solve this eigenvalue problem here. Hardest part of the problem. I calculate a charge density knowing these orbitals or these wave functions. I calculate the Hartree potential. It can be written as Poisson's equation. I get the exchange correlation potential and I get an output potential. Now if I'm really lucky, my guess was so good that this input potential and the output potential agreed. I write up my paper, everything is fine, the birds are chirping. That never happens, okay? Because if it really happened, you wouldn't do solid state physics, you'd do atomic physics. You'd say, I just get the potentials from the atom and it's good enough. Well, they're not good enough. So what you do is you go back and you iterate. Now, the hardest part in all this thing is this solving this eigenvalue problem. It's 99.9% of the work. So that's where we put in 99.9% of our efforts to make this practical quantum mechanics work. And what we do is we rely on high-performance computing. So I deal with computer scientists. We came up with new algorithms to solve that eigenvalue problem very quickly. I thought about inflicting that on you, but I decided, well, I don't think I want to spend the next 10 minutes talking about computer science. So let me just give you a quick overview. What we do is we do not solve the problem eigenvalue by eigenvalue. All we determine is the density. It's a method called subspace filtering, and trust me, I'm beginning to sound like an American politician, we can get 2 to 3 orders of magnitude improvement over standard methods. So instead of doing maybe a 10 or a 20 atom system, we can now do a 1,000 atom system, maybe even 10,000 or more. You can find the references here. The last one was written in 2012, and we have a website here. We'll even give you the code. We're a very generous lot, and I don't guarantee we'll help you run the code, but we'll give it to you. Okay, so what can we do with this thing? Well, we can do a lot with this. Once we've solved that problem, let me go back just a second. Once we go back to this equation here, we know the spatial and energetic distributions of the electrons. We can calculate the total electronic energy. We can do a wide variety of materials properties. Okay. So here's an example. Remember I told you that we had that Heisenberg description, and I said that if you made really, really small nanocrystals, the optical properties would change. Okay, here's a calculation. It was done for silicon. Here's the largest one we've done. It's silicon 8,453, hydrogen 1,716. Why do we have those hydrogens in there? Well, we want to cap off these dangling bonds. We want to have a nice crisp gap, and we don't want to have anything that's chemically active at the surface. So we have roughly 10,000 atoms, roughly 40,000 electrons. We put 2 electrons in each wave function because we don't have to worry about magnetism. That means we have to solve for 20,000 eigenvalues. Child's play. Okay, so here's the energy gap there that we calculated. There's these x's here, and then we fit a power law, and it looks very similar to what you would have gotten from the Heisenberg uncertainty principle, except it's a little bit shallower. It goes more like 1 over the size of the nanocrystal, or 1 over the diameter, and I'll explain that if anybody's interested. These points down here, and I'm sorry I forgot to put the experiment, but these are experiments down here, so that's good. This crystal here, this is an old result. This crystal actually belongs out here. Now, typically this is a really hard problem for us, but our goal is to do 20,000. The Japanese, using similar techniques to what we've done, has done 100,000. They didn't do it fully self-consistently, so there's hope for us. Okay. There are a lot of applications. And I thought about doing all of them, but then I figured, well, you didn't want to spend 3 hours listening to this. You want to spend a half an hour listening to this. But these are things that we can do. We can look at phase stability. We can look at which crystal structure is more stable than the other. We can look at molecular dynamics. We can do liquids. We can do liquid aluminum. We've done liquid semiconductors. We put the liquid in a box. We calculate the forces, and we move the atoms around. We can do elastic properties. We can do interfaces, defects in these materials. Well, you can read the list. I like this one here. We can simulate the forces between things like scanning tunneling microscopes and atomic force microscopes, and we can do that too. All right, and we also do magnetic materials, so we can look at the evolution of magnetism. I'm not going to show any of that. I'm going to show one thing. I'm going to talk about an interface. Why are interfaces important? Well, I like this quote. It was done by Herb Kromer when he won the Nobel Prize in 2000. He said, the interface is the device. So I'm going to show you with the remaining few minutes what this interface, an interface might look like and how we might go about calculating it. You should get excited because I'm going to show you a gap, a material with a gap like silicon, interfaced with a material that has no gap, like lead. Okay. So what we're interested in is looking at electrons at the atomistic limit, and we're going to look at the properties of a metal semiconductor device at the nanoscale. And the one we're going to look at is called a Schottky barrier. It's an interaction of a metal like lead with a material like silicon. It's important because whenever we have these semiconductors, we have to take electrons, move them into the semiconductor, or move them out of the semiconductor. So it's important to understand this interface. Okay, now why did we choose to do lead on silicon? Well, lead does not form a silicide, so we have a very abrupt interface. That helps us understand the geometry. Oh, by the way, parenthetically, you tell me the geometry and I can do really huge systems. You tell me you have a bunch of atoms interacting and I don't know what the structure is. That's where there's a bottleneck these days. But we know the structure here. It's going to be a crystal lead on crystal and silicon. Okay, it's an abrupt interface. There's a lattice mismatch that we have to deal with. The lead atoms and the silicon atoms aren't the same size. So 10 lead atoms line up with 9 silicon atoms. That makes the problem hard. Okay, so here's an example. Here's a little cartoon. These gray guys here, what else? They're lead. And then they come right up here to the silicon surface, and they don't flow back and forth. They maintain this abrupt interface. And then we have these silicon atoms below. Now, there's a lot of atoms involved here, because if I do 10 lead atoms by 10 lead atoms, typically that's what I do, as opposed to 9 silicons by 9 silicons. On average, each layer has about 100 atoms. So there are 1,500 atoms. I always like to point out that when I was a graduate student, if I could do 10, I was happy. And now we're going to do 15. And we're going to relax the system. We're going to move all these lead atoms around. We'll fix the substrate and determine what's the lowest energy configuration. Hopefully, it'll resemble something that looks like experiment. Okay, so here's an example of how we might do that. The pinky atoms here are the silicon. This is one monolayer of lead over those. Now, because they don't line up, they're incommensurate, you can get a lead over sort of a hollow in between the silicon atoms. When that happens, the lead atom sinks into the substrate. So that's blue here in our color scale. When the lead atom resides right on top of a silicon atom, that pushes it out and that makes it red. Here's a picture of the corrugation. You have about 1/10 of an angstrom. It goes up and then it goes down and then it sort of heals. So when you get out to a dozen layers, all right, 9, 10, 11 layers of lead, not much is happening. I want you to remember 7 layers, and I'll explain why in just a second. So we've got a pretty good view of what happens here. We solve this problem self-consistently. We let the lead electrons move over and make friends with silicon. We let the silicon electrons make friends with the lead. And then we can calculate what goes on. Now we need some theory. Okay, and here's probably the most complicated slides I'm going to show you, not to fear. The left side is the metal lead, and the right side is the semiconductor. This is one of those energy band diagrams. On the lead side, we have no gap. There's something called the Fermi level here. That's the highest occupied state. So we have lead band occupied here, empty here. On the right-hand side, we have a silicon semiconductor. There's a gap. And so if I wanted to take this lead electron and move it over here into the silicon region, I can't do it because this region is forbidden. It's the gap. So I have to take that electron and move it up into the conduction band. Then I can conduct electricity. The mechanism that this results in is called a diode. It allows electrons to flow in only one direction. And the barrier to make those electrons flow is called the Schottky barrier. Well, if you look here, this energy to take an electron out to the vacuum, that's the work function. To take an electron from the vacuum and drop it in on the silicon side, that's the electron affinity. This Schottky barrier here is the difference between the work function and the electron affinity. So now if I put different metals on the same substrate, same semiconductor, suppose I did gold, aluminum, copper, in addition to doing something like lead, the Schottky barrier would depend on what this work function was, but not the substrate, which I'm holding constant. There's something called the S factor, and it's simply the change in the Schottky barrier divided by the change in the work function. So for Schottky-Mott theory, this number is 1. Okay. But there's another theory. And in point of fact, this theory doesn't work very well for something like metals on silicon. What you find is that this value here of S is about 0. Well, it took a guy with 2 Nobel Prizes to figure this out, John Bardeen. And Bardeen said, oh, that's just to remind you what S is, sorry. We'll get to Bardeen. Bardeen said, no, 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 no. On this silicon side, there are defects in here. There are surface states. There are states that lock up. When I move an electron from the metal in over here, I can't move this Fermi level back and forth. I can't change the Schottky barrier. This S factor vanishes. So we've got 2 theories. Which one works? Maybe neither one works. We're going to do quantum mechanics. We're going to find out. Okay, so here's the answer. If Schottky is right, along with Mott, then I look at the work function here. Well, the work function for a free lead film, it goes up, it goes down, it oscillates. So that's what I would expect the Schottky barrier to do. If I put 1 layer down, 2 layers down, 3 layers down, 4 layers down, it's going to oscillate back and forth. Does it oscillate back and forth? Well, yes and no. What we found is the following. For very low coverages, this is the number of lead layers, the Schottky barrier goes up and then it goes down. Hey, that's what the work function did. Great. However, for coverages, remember the magic 7? If I put down a large number of lead layers, it's almost flat. So in this region over here, it looks like the Bardeen theory works. Over here, it looks like the Schottky-Mott theory works. Okay, that's my example. My example is that without doing these quantum mechanical calculations, even for a simple system here, electronics at the atomistic scale, I don't think we would have known this. In fact, I know we wouldn't know this. And it also tells us that if we want to change the Schottky barrier, because for big layers of lead on silicon, it's pinned here. By the way, this number we calculate is correct, more or less, compared to experiment. But if I wanted to change the Schottky barrier, I could do it, and I know how to do it. And I know how these metal semiconductors interact. So that's my example. And as I said, we've got a number of different examples. Okay, well, I think I better finish up. First of all, I have to thank people for the support. I want to thank the Institute for Computational Engineering and Sciences for establishing a center in computational materials. Most of the support we get is for this effort that I've shown you is from the Department of Energy. We're also working on a National Science Foundation on magnetism, which I didn't talk about at all. I want to say a few kind words for the Department of Energy because I heard some disparaging remarks the other day. Hey, they're my friends. And one of the things the Department of Energy has done, and to a lesser extent NSF, is to provide funding for coding. Now, you might have said, well, wait a minute, people have been writing codes for a long time. But in the past, it was one of these things you said, I had an application that I'm going to do coding on the side. That's not true anymore. You can get coding, you can get funding to do coding. And one of the projects we have is to calculate all those gaps. Okay, photovoltaics, batteries, all sorts of applications, as Emily Carter mentioned. Okay, the computational effort is done at the Texas Advanced Computing Center and the National Energy Research Supercomputing Center, which is the DOE facility. Now, I sure as hell didn't do all this work myself, and this is a small smattering of the people that really helped me, but there are two people here that I want to bring special attention to. This man in black here is Joseph Saad. Joseph Saad is a computer scientist. He's a professor at the University of Minnesota. He's an expert on the eigenvalue problem, and I would say roughly 99.8% of what I know of computer science came from a collaboration with Joseph, which is ongoing for 25 years. This person here right next to him that says Texas is at SMU, and this picture was taken at Minnesota. So I should have known something when I was at Minnesota that there was a Texas in my future. That's Yongkai Zhao, and he did a lot on making those algorithm codes run really fast. The person who did the lead on silicon is Xuliang Chan. And I have one other thing. I want to talk about the future. Of course, somebody's always said that making predictions is difficult, especially about the future. But there are two megatrends going on here with respect to materials. One is the computers are getting better every year. They're getting harder to use, but they're getting better and better and better. One of the efforts that we've done in the Department of Energy is that our code is one of the first codes that's being brought up on a second-generation machine. And I haven't gone into any details, but the attributes of our code are very special. They're targeted at nanoscale structures. The other thing is the need for materials, and my gosh, that's what we've been talking about for the first few days. It's another megatrend. So my goal in life is to change all of you into quantum mechanics so we can address these problems, we can understand new materials, we can maybe even predict new materials. Okay, thank you very much. You've been a great audience.
Are there any questions? Yes, sir. Bob Skelton, A&M. You mentioned in the Dirac quotation that the physics is known and now we must compute.
Yeah.
Now, if you have all of these computations to do, and there are lots of them, how do you discount or do you discount computational error? So how do you know whether to believe what you're getting from the computer?
Oh, it's the old validation and verification. Okay, a couple of comments. First of all, when density functional theory came out, people call it an ab initio theory in the sense it's not based on experiment. But nobody really knew how well it was going to work. And the only reason people knew how well it was going to work was because people in solid-state physics like Marvin Cohen rolled up their sleeves and calculated materials and then compared to experiment and said, hey, we get a lot right. And the chemists did the same sort of thing. There's this fellow Becca who looked at bazillions of different molecules and compared to density functional theory. I'm picking on density functional theory because that's the one that's the most suspect. We know that density functional theory doesn't get things entirely right, and we know that because we've rolled up our sleeves and done computation. There's another issue, though. Let's say we accept density functional theory for all its flaws, and we have some experience to know when it works and when it doesn't. I showed you, well, could you show me slide? I brought some extra slides. If I can't find it immediately, then to heck with it. 37? Can we get 37? Yeah, thank you. So what we did this 10,000 atom structure. How do we know that's right? Nobody else has ever done 10,000 atoms. Well, this inset over here is the distribution of states. It's like a histogram, how many states there are per each little bin, except it was done for crystalline silicon. So my student about a year ago said, okay, I've done this atom here, and I said, well, let's see how it agrees with bulk silicon, because it's bloody big enough, it ought to look like bulk silicon. So he sent me this file with 30,000 entries in it, and I said, well, that's nice. And I made a MATLAB plot, and when I plotted up the MATLAB code, I said, holy Toledo, we're right on the money, because I couldn't have drawn a figure any better that looks like those two. So what we do is we test against other codes, we test against experiment, we do molecular and when we do molecular dynamics, we check things like energy conservation. So we have our ways. But what you raise is what I try to instill in my students. How do you know that the computer's not giving you garbage? Because computers can throw out a heck of a lot of numbers very quickly, and they might not mean anything. So we compare to experiment, we compare to limiting cases, and we compare to other codes.